All right, we got a quick one for you here for part two. We've done very similar problems here today. We've just never really thought about them in terms of differential equations. And so what we're going to do here, remember differential equations is when I'm going to give you, instead of giving you a function, I'm going to give you a function that represents the derivative of some other function. And we're going to do tangent line approximations. So remember what tangent line approximations say is if I have some function f of x, and I want to know, I'm really interested to know what this point is right here. And say I don't know that point, but I do know two things. Say I know this point right here, and I know the derivative of the function. I know the slope of the tangent line. Well, the idea of a tangent line approximation is, you could do worse. It's a good approximation to just say, well, I'm going to pretend the function keeps going off in the same direction of the tangent line. And, over tiny distances, this is not a bad approximation for a lot of functions. And so in order to do that, we need an anchoring point, right? We need an anchor and we need a direction. And so let's see what we have here. The quantity of a substance can be modeled by the function q of t that satisfies, so that has a differential equation dq dt. So the instantaneous change in q over the instantaneous change in t is negative 1/50th q, right? So remember, this is like those previous problems. This is interesting. The derivative of the function actually doesn't depend on t at all. It depends on q, right? So the derivative actually depends on the output of the function, which is really interesting. One point on this function is q of 2 equals 200. Based on this model, use a linear approximation of the graph at t equals 2 to estimate the quantity of the substance at t equals 2.2. Okay, so here's the basic way that these problems work. We want to write an equation in point slope form. Y minus y1 equals x minus x1. Well, we actually already have x1 and y1. x1 equals 2, y1 equals 200. They told us that when x is 2, y is 200. Okay, great. And we can use the differential equation to find the direction, right? The instantaneous rate of change, the derivative is the slope of the tangent line of this function. Well, super interesting, right? The derivative doesn't depend on x, right? That's what makes these weird, but it is the derivative nonetheless. dq dt, and there's a little notation here. You're going to write kind of like a line, and then I'm going to say at q, or let's say dq dt, we know is negative 1/50th q, right? And so I'm going to say this is at q equals 200 equals negative 1/50 times 200, right? So you just have to really notice here, sometimes the derivative will depend on x, sometimes on y. In this case is negative 4. And so what we'd have here, we'd have y minus 200 equals the derivative, negative 4 times x minus 2. And remember the way we did these before, this is the equation of that tangent line at x equals 2. We can plug in 2.2. So we're going to take this 2.2 here. We'd have y equals, I'm going to move that 200 over now, 200 minus 4 times 0.2. I'll write this out. 2.2 minus 2. Y equals 200 minus 4 times 0.2. What's 4 times 0.2? 0.8. Y equals 200 minus 0.8. Y equals 199.2, right? And so the idea is basically, right, just back up for a second. The best approximation we can do is we say, okay, when x is 2, y is 200. What's it going to be? What's q going to be when x, or in this case t, is 2.2? Well, we do know it's heading down because the derivative is negative. So we move a little bit down. We move down from 200 to 199.2. It's the best we can do. Let's see one more real quickly here. let's say we have, and so now just kind of abstracted completely from context here. If we have the derivative of the function dy over dx equals x squared plus or x squared times 2y plus 3 squared, ooh, tricky one, with a particular solution of y equals f of x, okay? Initial condition, use the equation of the line tangent to the graph at the point 3, comma, -1. So we have y minus -1 is the slope m times x minus 3. We just need to figure out the slope using this differential equation. Well, we just need to plug in x is 3, y is -1. So we say the derivative of y with respect to x, and so this is a really common notation here. You'll see the point listed down here, 3 comma -1, right? The reason you list the point and what makes differential equations interesting, like I said, is that the derivative depends on both x and y. So it's not just at any x value. The derivative changes depending on where you are up and down. So these aren't just lines anymore, right? These are a little bit more complicated. And so what we'd have here, we'd have 3 squared times 2 times -1 plus 3 squared. We'd have 9 times, this is going to be -1 squared, and so we'd have 9. So we'd have y plus 1 equals 9 times x minus 3. So we could solve this for y. We could have y is equal to 9 times x minus 3. Oops. Y is equal to positive 9 times x minus 3 minus 1. Now remember, we don't actually want to distribute that yet because our life is actually made a lot easier by the fact that if you plug in 3.1 for x, we're going to have y equals 9 times 0.1 minus 1, y equals 0.9 minus 1, y is equal to -0.1. And so let's just think, okay, did that pass the smell test? Well, when x is 3, y is -1, and the derivative of the function at that point is positive 9. And so our function should be going up over the space from 3 to 3.1, and it does. It goes up from -1 to -0.1, passes the smell test.